So the last lecture we talked about our ocean currents, ocean gyres, and how they affect our climate. Why we have such awesome weather here in California. It has to do with the fact that we have a cold current right off our coast. Not always perfect for surfing in. You have to wear a wetsuit, but it makes our summers here beautiful. But one of the things I didn't really mention yet is that these currents do have some variation to them. And this actually is caused by something called the Walker circulation. So a few lectures ago, we talked about the three-cell model of the atmosphere. We talked about the Hadley cell, the Ferrel cell, the polar cell. But actually, near the equator, there's another major circulation that has really important implications on our weather. And it's called the Walker circulation. And as meteorologists, we actually use this Walker circulation to indicate the presence of El Nino and La Nina. Now, those are buzzwords for us oftentimes, and I'm sure you've heard of them before, and maybe even have your own idea of what they are. Usually in my face-to-face classes, I always ask, so what is El Nino? And I usually get some kind of response in the form of, oh, it's a storm, or it's like a big hurricane. Well, actually, El Nino and La Nina are both different phases of the Walker circulation. And they both have major implications on our weather. So let's talk about this. So first, let's start in the Pacific Ocean, right near the equator. This is where all of this takes place. So we have the Eastern Pacific, which is where we are, which is where North, Central, and South America is. And then the Western Pacific, that's where East Asia and Australia are, and Indonesia. And along this region, we have the trade winds. The trade winds blow from east to west. As they blow over the ocean, they push that warm surface layer of the ocean towards the east, where it then bunches up, towards the west, where it then bunches up on the western end of the Pacific Ocean. And what you get is you get this big bulge of warm water in the Western Pacific. On the other hand, when that top warm layer is skimmed off over in the east, what takes its place is cold water from below. So we get this cold water that's present in our East Pacific. Now, if you remember from the two-column model, so I told you we're going to see this a lot. Warm water leads to warm air. Warm air leads to rising air. So we get lots of rising air in the Western Pacific. This results in low surface pressure. This results in the development of thunderstorms. So the weather in the Western Pacific is typically very stormy, and the pressures there are typically very low. On the other hand, in the Eastern Pacific, typically the waters are much cooler. Cooler water leads to cooler air, leads to sinking air. This leads to very calm weather, very dry weather, and high pressure at the surface in the Eastern Pacific. And so the Walker circulation looks something like this. Don't mind the speed of it, but basically what happens is the trade winds blow water to the west. You then get this bulge of warm water, which creates a bulge of warm air. That warm air then rises. You have low pressure down here. Meanwhile, in the Eastern Pacific, you have cold sinking air and high pressure near the surface. You have high pressure near the surface. And so the weather is typically very dry. Now, this is the normal setup. This is what I would call la nada, basically the nothing. So I don't use a lot of slang in my class, but this is some slang I will use. La nada means the nothing. We are neither in El Nino nor La Nina. But actually, as scientists have observed this region a lot more, and over the last 30 years we've had three very major very major El Ninos, We've had 3 very major El Ninos, and we've actually had some major La Ninas as well. We've actually discovered that what's happening is the ocean and that water circulation are constantly in a state of flux, a state of oscillation between El Ninos and La Ninas. So this normal setup, this La Nada setup, basically just represents sort of the in-between. We're not quite in an El Nino, but we're not quite in a La Nina. And in this case, in this normal sort of everything averaged out case, we get that water circulation that I just talked about. We get that. Winds travel from west to east. That pushes warm water to the west. Or I say west to east, I meant east to west, sorry. Warm water travels from east to west. That creates a lot of rising air in the western Pacific, a lot of sinking air in the eastern Pacific. So that's our normal, that's our baseline. That's our normal setup. That's our normal setup. However, and it looks just like this. However, in the case of an El Nino, that whole circulation reverses. So let's talk about what El Nino is and where the name came from. So basically what happened was South American fishers started to notice that during certain years, fishing would be really bad in the months of November, December, and January, right around Christmas time. Hence, whenever that happened, they would call it El Nino to refer to the small boy. Specifically, they were making references to Jesus and making references to Christmas. That's just where the name came from. So El Nino came from that. With that said, they didn't fully understand why it was happening, but what was actually happening was the ocean waters over the eastern Pacific were much warmer than average. Much warmer water actually has much less nutrients in it. Much less nutrients meant much less fish. So they would have a lot of worse fishing occurring during those times. Well, here's what actually happens. What actually happens is that typical east to west trade wind that we talked about actually begins to slacken off. And then sometimes it even reverses. This diminishes the amount of warm water that's pushed to the west. Instead, all that warm water that was moving to the west sloshes back to the eastern Pacific. And so now we have warmer than average ocean waters over the eastern Pacific. That then results in more rising air and stormier weather. Now what's interesting is here in California, when we talk about El Nino, we think about torrential rainfall, very stormy weather. That's what people think El Nino is a storm. But that's only true here in California. If you actually go to the western Pacific, to places like Indonesia, Eastern Australia, East Asia, because the waters there end up becoming colder than normal, since they don't get all that extra warm water from the East Pacific, what ends up actually happening is they get less rising motion there and much drier weather. So while El Nino means storms for us here in California and along the Eastern Pacific, in the Western Pacific, it's a lot drier. And in fact, they oftentimes get droughts during that time. So in an El Nino, as I mentioned, what actually happens is the trade winds that were blowing from east to west slacken or even reverse. So now we get this west to east movement. There's a current that develops called the equatorial countercurrent. And this allows all that warm water that was bunched up here over the western Pacific to actually slosh over to the eastern Pacific. This then creates lower pressure here, more rising air, and stormier weather. Meanwhile, over here in the West Pacific, it's a lot drier. So this actually has major implications on weather, not just here in California. As a matter of fact, This kind of creates a slight butterfly effect in that the changing circulation here then results in changing circulations around the world. For example, the increased storminess in the eastern Pacific actually creates much stronger wind shear in the West Atlantic. That actually results in less hurricane formation there. And as I mentioned earlier, this sinking air here in the West Pacific results in much drier weather over near Australia and Indonesia. So there's actually global implications of El Nino. Here are some of them. So while we're over here nice and wet, usually a little bit cooler than average, over here in the Western Pacific, it's a lot warmer and a lot drier. Meanwhile, places in the Pacific Northwest tend to be a lot drier as well. Places along Alaska tend to be a lot wetter. Interior Siberia and East Asia becomes a lot colder. Areas down along the western coast of South America, some of the driest places in the world, actually become wetter. In fact, during the last major El Nino, the Atacama Desert, one of the driest places in the world, actually started blooming. There were flowers blooming in the middle of the desert because of how warm and how wet it got there. And these are just a few examples. But what about us here in the United States? Well, here in the United States, El Nino amplifies our Pacific jet stream. It amplifies that subtropical jet that I said otherwise isn't very important, but it actually amplifies it. And as it amplifies it, as it actually makes it a much stronger jet stream, because you now have all that warm water here, so there's a bigger boundary between warm and cold, you end up getting more storms that develop on it. And usually these storms march right into California. So most of California gets really wet during an El Nino. Now, what about the opposite? So sometimes, rather than slackening off and dying off, we'll actually have a situation where El Nino, or where the trade winds, will instead strengthen. This is called La Nina. And this is just the opposite of El Nino, hence the name. The name is just there to represent that this is the opposite of El Nino. And so they use the name La Nina. Basically what happens here, the trade winds strengthen, and so even more warm water blows to the Western Pacific. So in a normal setup, some warm water is blowing to the Western Pacific. In this case, even more, extra warm water blows over there. So the waters over in the Western Pacific become even warmer than average. Therefore, there's more heat, there's even more rising air, there's even stormier weather. Meanwhile, what we're left with here is much cooler waters than average, much more sinking air in the Eastern Pacific, and much drier weather. So even drier than average. And so this is what La Nina looks like. It's basically just an intensified Walker circulation. So in an El Nino, the Walker circulation reverses. In a La Nina, the Walker circulation intensifies. It intensifies. And the consequences of La Nina are basically the opposite to El Nino. Places that were warm are now much cooler. Places that were dry are now much wetter, such as Eastern Asia, Indonesia, and Australia. They're now much wetter. So instead of getting droughts, there's usually major floods here. Meanwhile, over here in the Eastern Pacific, it's a lot drier. It's a lot drier. And then here in the United States, that Pacific jet stream, that subtropical jet stream that gave us all that rain in El Nino, basically just falls apart. And instead, a high pressure ridge builds that pushes our storms much further to the north. And this actually gives the Pacific Northwest even more rain than it normally gets. So just to review, I'm going to go back a few slides here. In the case of El Nino, the Walker circulation reverses. In the case of La Nina, the Walker circulation maintains its normal cycle, but instead it intensifies. The last thing I wanted to talk about is the California drought. So if you've been living here in California for more than a few years, you know that we just emerged from a really severe drought. And we were actually on the verge of going back into it until we had a nice wet March and April this year. Well, the California drought was a string of very dry seasons, 2012 to 2013, 2013 to 2014, and 2014 to 2015. And they were all three of those dry seasons were caused by the same thing. Basically what happened was there was a large body of very warm ocean water off the northeast Pacific, off of the coast of Seattle, Portland, off of British Columbia, southern Alaska. There's this giant body of warm water. This warm water results in rising air, and therefore high pressure aloft develops. That actually caused our storm track, that jet stream that, as I mentioned a few lectures ago, acts like a freeway. It basically caused it to take a big northward kink, and then it turned back down to the south across the central United States. What we actually experienced was much warmer and drier than average weather here on the west coast of the United States. Ironically, what goes up must go down. On the other side of the country, in the eastern half of the United States, I'm talking about cities like Chicago, St. Louis, Cleveland, Buffalo, New York, Albany, Boston, New York City, Washington, D.C., all of those major eastern cities actually experienced 3 years of record cold. Record cold. In fact, there was this phenomenon that many people referred to as the polar vortex that took hold of the eastern half of the United States. And in fact, some people would actually come out and say that, oh, well, this means that global warming is fake. Meanwhile, here on the West Coast, we had fires in January. Normally during our wet season, we were having fires and 90-degree heat and records, and this happened for 3 consecutive years. And again, it all happened because this storm track, which is caused by our jet stream, normally travels straight across. We get what's called a zonal flow normally. But during these 3 years, this huge ridge of high pressure pushed the storms up and over the California coastline. And so what we ended up having was regions along the west coast were much drier than average. A colleague of mine, Daniel Swain, he used to work at Stanford, I think he works now at UCLA, actually coined this ridge the ridiculously resilient ridge. And if you Google search it, you'll actually see some of the work that he's done. And there are suggestions that this may be tied to climate change. Now, I wouldn't go that far, but I would say that it's possible. But really, the concern regarding this came from the idea that this ridge developed at the same time as a warm body of water here in the northeastern Pacific. And we called this the blob. Basically this giant blob of warmer than average waters. And this creates that warm air, which could then create a ridge. These two things, this big ridge and this blob, ended up creating a symbiotic relationship between one another. The ridge kept things warm, that kept the ocean warm. The ocean staying warm caused more rising air, which kept the ridge in place. And this just kept in place for a long period of time, for much longer than normal. one of the things that we as meteorologists are starting to try to figure out now is which came first. Did we start with the ridge and then that created this blob, or did we start with the blob and that led to the ridge? There will be more research done on this in the years to come as we begin to really ask ourselves, was that drought a new normal? I don't have an answer for you, but I don't think it looks too well. Well, that's it for Module 6. As always, if you have questions, comments, concerns, please reach out to me. And if, just a reminder, look over those review sheets. Look over the Module 6 review sheet as you prepare for this week's module quiz, if you're in my online class. If you're not in my online class, I hope you enjoyed this video. If you are in my online class, I still hope you enjoyed this video. Thank you for watching.